This is Katie Bowman's AP problem number 7. So let's start off by reading the question. Answer the following questions that relate to electrochemical reactions. Part A, under standard conditions at 25 degrees Celsius. I'm going to turn this sideways really quick. Okay, under standard conditions at 25 degrees Celsius, Zn reacts with CO to produce CO solid. Part 1 asks to write a balanced equation for the oxidation half reaction. So Zn is the one oxidizing because its charge goes up by 2. So Zn goes to Zn2 plus 2 electrons. And then part 2, write the balanced net ionic equation for the overall reaction. So that is Zn solid plus CO2 plus aqueous yields CO solid plus Zn2 plus aqueous. And then part 3 says calculate the standard potential E for the overall reaction at 25 degrees Celsius. So we go to part B, and we use the equation delta G equals negative NFE. So N is number of moles of electrons, F is Faraday's constant, and then E is what we calculated in part 3. So we use delta G equals negative 2. We use 2 electrons in our total equation. And then Faraday's constant is 96,485. And then our E that we got was 0.55. So that gives us 106.1 joules. Alright, so then the next part of part B asks us to determine the value of the equilibrium constant K for the reaction at 25 degrees Celsius. So we use the equation log of K equals Ne over 0.0591. That's our constant. That's why we use that number. And then N is the same number of moles of electrons, and then E is the thing that we already got, the standard. So log of K equals 2 times 0.55 divided by 0.0591, which gives us 3.98 times 10 to the 18. Alright, and then the next part of that asks us the standard reduction potential of E for the half reaction O2 plus 4H plus 4E minus yields 2H2O has a value of 1.23 volts. Using this information in addition to the information given above, determine the value of the standard reduction potential E for the half reaction below. So it gives us a half reaction and this half reaction, and then it wants us to find this reaction here that it gave us in part B, like in the beginning. So what we do for this, let me grab this paper. So this is the whole thing that we're going to do. So we're going to use the 2 half reactions that they gave us, and then we are going to change them around using the Hess's law idea to get this reaction here. And when we look at our standard reduction table that we have, we see that, or actually we didn't have, just kidding, we didn't use it because they gave us the values. So initially this lower one here was 0.55 volts, and then the top one, the top reaction right there, was 1.23 volts. So we're looking for X right here, which is this one. So what we're going to do for this, like this reaction, we're going to flip it and multiply it by 2. But you don't change your E value when you like change the reactions around. You only would change the charge, but you wouldn't multiply it by 2 like you would normally do if you were doing regular Hess's law. So you end up getting negative 0.68, but since we're looking for this version of it, we're not looking for the flipped version, you end up flipping it back, and then it becomes positive again, because you're not looking for the flipped version of it, because that would kind of change it. So yeah, that's what you get. You get 0.68 when you do all that. Okay, and then let's look at what part C asks us. In In a electrolytic cell, Cu is produced by the electrolysis of CuSO4. Calculate the maximum mass of Cu that can be deposited by a direct current of 100 amperes passed through 5 liters of 2 molarity CuSO4 for a period of 1 hour. So we're going to start at 1 hour and we're looking for grams of Cu solid. So we know that in 1 hour that's 3,600 seconds. And then we need to cancel out seconds. So we can use amperes, which also is coulombs over seconds. So we can use that, and it gives us 100 amperes. So it's 100 coulombs over 1 second. And then we use Faraday's constant, which is coulombs also. So that's 96,485. And then we can put it over 1 mole of electron, because that's how it is in Faraday's constant. And then we need to cancel out the electrons. So we're going to use 20 moles of electrons, or it's like a 1 to 2 ratio of moles of Cu to moles of E. When you look at the reduction table that you have, it's a 1 to 2 ratio. So it's 20 and 10, and then you need to cancel out Cu, so you're going to use 1 mole. And then you need to convert it into grams, so you put 63.55, and when you multiply all of that all the way through, you get 118.5 grams of CuS. And that's all. Bye.